Namaste dosto. Imagine you are navigating your way from home to your school. You don't just want to know how far it is, but also which direction to head. Now, this idea brings us perfectly to today's topic. Vectors, quantities that carry both magnitude and direction. This is very different from scalars, which only tell you how much, but nothing about which way. So, what exactly is a vector? Simply put, a vector is a quantity that has both size and direction. You will see vectors written in two common ways. One is with bold letters like vector or vector v, and the other is by putting an arrow on top, such as vector AB. Vectors are fundamental in physics and math because they describe physical quantities like displacement, say, moving from one point to another, velocity, which tells you speed along with direction, and force, which pushes or pulls in some direction. Picture a simple coordinate axis with a point A and a point B. An arrow from A to B shows displacement. It has both how far and which direction you went. That arrow is your vector. Keep this image in mind as we move ahead. Let's build on that by classifying vectors based on their properties. There are several special categories you should know. First, the zero vector, denoted as vector 0, is the unique vector with zero magnitude and no definite direction. Then, there is the unit vector, a very important type, which always has a magnitude of exactly 1. We use unit vectors to define directions only without worrying about length. Next, we have collinear vectors. These lie along the same line, so they either point in exactly the same direction or exactly the opposite direction. Think about when two vectors are equal. They must have the exact same length and direction. But interestingly, it doesn't matter where they start. And what about the negative vector? If you have a vector A, then its negative, written as minus vector A, has the same length but points exactly the opposite way. Visualize arrows on a coordinate axis showing vectors that are equal and vectors that point oppositely, like one heading east and the other west, but both with the same size. That's how these different vector types look. Now, let's talk about position and displacement vectors. Very handy for locating points and understanding movement in space. The position vector of a point, say point P with coordinates x, y, and z, from the origin O is written as vector OP equals x times I hat plus y times j hat plus z times k hat. Here, I hat, j hat, and k hat are the unit vectors along the x, y, and z axis respectively. If you want to find the displacement vector between 2 points A and B with coordinates x1, y1, z1 and x2, y2, z2, you subtract the components. Vector AB equals x2 minus x1 times I hat plus y2 minus y1 times j hat plus z2 minus z1 times k hat. This tells you not just how far you've moved, but in which direction, making it very useful for calculating both magnitude and direction of travel through three-dimensional space. Imagine a 3D coordinate system with vectors OP, OQ, and PQ representing positions and displacements, very neat and visual. Next, let's explore how vectors can be combined and scaled. Much like numbers but with a twist, we have to keep their directions in mind. The addition of vectors is straightforward. You add their corresponding components. So if vector has components of 1, a 2, a 3, and vector B has B1, B2, B3, there's some vector A plus vector B equals a 1 plus B 1 times I hat plus a 2 plus B 2 times j hat plus a 3 plus B 3 times k hat. Similarly, when you multiply a vector by a scalar k, you simply multiply each component by k. So, k times vector A equals k times a 1 times I hat plus k times a 2 times j hat plus k times a 3 times k hat. It's important to remember that vector addition follows the commutative property, meaning vector A plus vector B is the same as vector B plus vector A. It also satisfies associativity. The grouping of vectors doesn't affect the sum. Plus, scalar multiplication distributes over addition. So k times vector A plus vector B equals k times vector A plus k times vector B. Picture this with the parallelogram law. Two vectors coming from the same point form adjacent sides of a parallelogram, and the resultant vector is the diagonal. This helps us see vector addition visually. Time to get comfortable with expressing vectors using components along coordinate axis. Any vector in three-dimensional space can be written as vector equals a 1 times I hat plus a 2 times j hat plus a 3 times k hat, where a 1, a 2, and a 3 are real numbers. Each component represents how much the vector extends along the x-axis, y-axis, and z-axis respectively. This breakdown makes it easier to deal with vectors mathematically. To find the length or magnitude of vector A, we use the formula. Magnitude of vector A equals square root of a 1 squared plus a 2 squared plus a 3 squared. Repeat after me. The magnitude of vector A equals the square root of a 1 squared plus a 2 squared plus a 3 squared. Visualize this in a 3D coordinate system. Vector A pointing somewhere in space, with its components projecting right onto each axis. That's how vectors break down neatly into parts we can handle. How do we describe the direction of a vector precisely? We use the unit vector and something called direction cosines. Given any vector A, you find its unit vector, denoted as a hat, by dividing vector A by its magnitude. So, a hat equals vector A divided by the magnitude of vector A. This unit vector points exactly in the same direction but has a length of 1. Direction cosines are the cosines of the angles that the vector makes with the x-axis, y-axis, and z-axis. We use the Greek letters alpha, beta, and gamma to represent these angles. So, the direction cosines are cosine of alpha, cosine of beta, and cosine of gamma. Interestingly, these cosines satisfy the equation where cosine squared alpha plus cosine squared beta plus cosine squared gamma equals 1. This relationship helps us understand and check the direction of vectors in space. Imagine the vector starting from the origin and making distinct angles with each of the three axes. That's what those direction cosines measure, giving us a complete picture of direction in 3D. Let's now bring all this into action with a quick solved example to calculate a displacement vector. We have 2 points, A at coordinates 2, -1, 3, and B at 5, 3, -2. Our goal is to find vector AB, which represents the displacement from point A to point B. Step 1. Write position vectors of A and B from the origin. Vector OA is 2 times I hat minus 1 times j hat plus 3 times k hat. Vector OB is 5 times I hat plus 3 times j hat minus 2 times k hat. Step 2. Subtract vector OA from vector OB to get vector AB. This gives us 5 minus 2 times I hat plus 3 minus minus 1 times j hat plus minus 2 minus 3 times k hat. Simplify this to 3 times I hat plus 4 times j hat minus 5 times k hat. So, the displacement vector from A to B is vector AB equals 3 times I hat plus 4 times j hat minus 5 times k hat. Fantastic! Imagine this vector shown on a coordinate system from point A to point B. You can see the direction and length shine through. Let's quickly recap what we have covered today. First, any vector can be expressed as A1 times I hat plus A2 times j hat plus A3 times k hat. Next, the magnitude of vector is the square root of A1 squared plus A2 squared plus A3 squared. Don't forget direction cosines, the cosines of the angles that the vector makes with the x, y, and z axis, satisfy the equation where the sum of their squares equals 1. Key ideas. Vectors carry both magnitude and direction, clearly different from scalars that have only magnitude. Vectors follow algebraic laws like commutativity and scalar multiplication. And importantly, any vector in space can be resolved into components along the basis unit vectors I hat, j hat, and k hat. Keep practicing these fundamentals. They are the building blocks for so much more in physics and mathematics.